In this lesson, we're going to talk about random variables. So a random variable is something that assumes a value based on the outcome of a random event. So it has to be assuming a quantitative number associated with it, okay? We're not talking categorical, and it's based on the outcome of a random event. We will always use a capital letter to indicate a random variable, okay? We then use little lowercase x's typically when we're talking about like a specific probability, like what is the chance that the random variable ends up being 1/2 or something. We have two types of random variables. We're going to start by talking about discrete random variables, and then we'll move on to continuous. So just like in previous math classes, a discrete would be where like you could count the individual occurrences. It could take you a long time, but you could specifically count them. Now continuous would be something like anything that could take on all the decimals, like between the numbers 1 and 10. Well, that's actually an infinite amount of values, so that's continuous data. You can't count that. There are two formulas that you're going to be using a lot when it comes to discrete random variables. The expected value is the same as the mean, okay? And here's some notation. Notice that we're using mu of x is equal to the expected value, and this is how it's calculated. We'll look more at this. And here is the standard deviation. Again, we're talking about a model, okay? So we use Greek letters or parameters to represent our mean and our standard deviation, and I'll talk more about this formula, but please take a second and look at where these are on your AP formula sheet. So random variables are easiest to understand with examples. So on Valentine's Day, the Quiet Nook restaurant offers a Lucky Lovers special that could save couples money on their romantic dinners. When the waiter brings a check, he'll also bring the 4 aces from a deck of cards. He'll shuffle them and lay them out face down on the table. The couple will then get to turn 1 card over. If it's a black ace, they owe the full amount. But if it's the ace of hearts, the waiter will give them a $20 Lucky Lovers discount. If they first turn over the ace of diamonds, hey, at least it's red, they'll get to turn over one of the remaining cards, earning a $10 discount for finding the ace of hearts this time. So we're going to construct a probability model. And before we do that, let's actually define our random variable. And again, we use capital letters. So I'm going to use a capital X, and what does it represent? Well, it's always a numeric value based on the outcome of a random event. So what's the numeric thing? It's the amount of discount, so it's the Lucky Lovers discount. Okay, so I set up a table here where I'm going to show my different outcomes, what the amount of the Lucky Lovers discount would be, so each individual lowercase x, and then the probability that my random variable is equal to each of these different outcomes. All right, so the best case scenario for a couple dining would be to get the ace of hearts. And how much money do they win for ace of hearts? Well, they get a $20 discount. And let's look at the chance of that happening. So there were 4 cards that the waiter would bring out, and your chance of getting ace of hearts would just be 1 out of 4. Now, there's another way that you could save $10. And how does that happen? Well, you have to first draw an ace of diamonds, and if you do that, you get to do 1 more card, and that would be if you then draw the ace of hearts. If you get that, then you get $10, and let's figure out that chance. And that chance, well, first of all, getting the ace of diamonds would be 1 out of 4. But you've drawn that card. It's not like you're going to lay it face back down on the table again. So now there would be 3 cards remaining on the table. So your new probability would be out of 3, and only one of them is a heart. So that would be a 1/12th chance of occurring. And now let's look at the third scenario where you don't get any money at all would be if you draw a black card. Well, there's 2 ways you can think this through. One way is just to use the complement, so it'd be 1 minus 1/4 plus 1/12, and that would actually equal 2/3. But often sometimes kids struggle with that because they're like, well, how can you get probability of 2/3 when I see that half the cards are black? So let me just encourage you to look at your sample space. So what I did here was I sketched a quick little tree diagram where you pick one of the 4 cards. So each of these would have a 0.25 or 1/4 chance of happening. So to see this, it might be easiest just to look at a quick tree diagram. So you have a 25% or 1/4 chance of drawing any of the 4 cards on your first draw when the waiter brings out the 2 red and 2 black. So if you draw a Queen of Hearts, this is a 1/4 chance, and that wins you $20. Now, if you draw the black card right here, that's a 1/4 chance, and that gets you $0, and this is a 1/4 chance and gets you $0. But where it gets interesting is if you first draw this diamond. You would have 3 cards remaining, so you could draw the heart, and that's a 1/3 chance. Each of these branches would be 1/3. And then this would be your black spade or your black club. So you would multiply your branches together. 1/4 times a third would be a 12th. 1/12 right here, each of these. So what's your chance of, and let me just say, so this one would win $10, and these 2 scenarios, you win nothing. So what are your chances of winning nothing? It would be 1/12 plus 1/12 plus 1/4 plus 1/4, and that would equal 2/3. So the probability of my random variable producing a $0 payout is going to be 2/3. Okay, so now you've seen 2 ways of getting the probability that x is equal to 0 is 2/3. So now it says, based on a probability model for the size of the Lucky Lovers discount the restaurant will award, what's the expected discount for a couple? So this whole expected discount should give you a clue that you're looking for the expected value. It's kind of like the law of large numbers. If we were to play this game many, many times on Valentine's Day and keep track of what the discount is over time, what's the expected discount? All right, so to do this, it's very logical, but you're also given the formula sheet. So what you need to do is take each random outcome here, the $20, and multiply it by the chance of it occurring. And then add that to, again, this outcome times the chance of it occurring, plus this outcome times the chance of it occurring. But I'm going to show you using the proper notation. So expected value is the same as the mean. So we write mu of x is equal to the expected value of our random variable, so I'm using capital X, which is equal to 20 times 1/4 plus 10 times 1/2 plus 0 times 2/3, which is equal to 70/12, or approximately 5.83. And let's put that in context. So I'm going to say that couples dining at the Quiet Nook can expect discounts to average $5.83. Now, no couple can have that discount, but this is, again, like our long-term average. What is the standard deviation of the discounts? So let's look at the formula for standard deviation. From your formula sheet, sigma of x is equal to the square root of sigma of each x minus the mean, square it, times the probability of the outcome occurring. Now, out of habit, I normally start with the variance, actually, rather than the standard deviation, because when we start combining random variables, you'll learn why we can't just combine standard deviations. We actually have to work off of the variance. So it's a good practice just to kind of get in the habit of doing the variance, which means I'm just doing everything without the square root sign. So I'm going to find the difference of each individual x value, or each outcome. So the first one was 20. I need to subtract the mean, which we just saw in the last part was 5.83. I square that and I multiply it by the chance of me getting a 20, which was 1/4. And I'm doing the summation. So plus, the second outcome was 10, minus my mean, square it, times the chance of that occurring was 1/12. And then plus, the last one was 0 minus the mean, 5.83, square it, times the chance of that occurring was 2/3. Okay, so take a second, type that in your calculator, and I get that the variance is equal to 74.306 approximately, and I just leave that value on my screen so that I don't round multiple times. And now I actually find sigma, or my standard deviation, by taking the square root of 74.306, and that's approximately, I'm going to go to the nearest hundredth, $8.62. So that tells me that couples can expect discounts to average $5.83, which we just found, with a standard deviation of $8.62. I'm going to show you a quick way to do that on your calculator now. So what I'm doing here is I'm putting the outcomes of my random variable, the 20, the 10, and the 0, and I'm putting the probabilities that correspond to it right next to it in the next cell. So it was a 1/12. So I can even just type the fraction and it changes it to a decimal to divided by 3. And there we go. All right, so get out of this and you're just going to actually run your one variable stat again. So stat calc and one variable stat, and you put L1, but then your frequency is L2, where you put the probabilities. And now I run calculate, and here it is. My mean is 5.83, and my standard deviation is 8.62. That's the two values I got when I did it by hand. Our second example is about Epgar scores. It says, in 1952, Dr. Virginia Epgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0-1-2 scale to rate a newborn on each of the 5 criteria. A baby's Epgar score is the sum of the ratings on each of the 5 scales, which gives a whole number from 0 to 10. Epgar scores are still used today to evaluate the health of newborns. So our question is, what Epgar scores are typical? To find out, researchers recorded the Epgar scores of over 2 million newborn babies in a single year. Imagine selecting one of these newborns at random. So we're going to say that our Epgar score is our random variable. So it's capital X is equal to the Epgar score of a randomly selected baby 1 minute at birth. So it could take on different values. It could take on any value from 0 through 10. Now this is discrete data because we're not giving these decimals in between. And you're given a probability distribution with all these chance values filled in, okay? And it's good to see that a lot of babies are we're higher up here in our probabilities, near 8 or 9, so healthy children that they're randomly serving. And Our first question is, write the event the baby has an Epgar of 0 in terms of x. Then find its probability. So we're just checking some proper notation here. So the probability that our random variable is equal to 0. So notice I'm using a capital X. What would it be equal to? Well, I can use my knowledge of probability adding to 1 to get this. So a little tedious maybe because I got 9 decimals I'm going to need to sum here. So I'm going to say it's equal to, and you know what, I'm going to be just a little bit lazy here rather than writing it all out. So take a second, pause, and please sum the numbers from 1 through 10 inclusive. I get 0.999. So this would equal 1/1000th. So now we're asked to describe or to first create a histogram of the probability distribution, and then we're going to describe what we see. Right? So I'm going to put my random variables along the x, and I'm going to put my probability along the y-axis. And I've sketched in my histogram here. So describe what we see. So think about when we're describing graphs, what should you talk about? Shape, center, spread, unusual features. We always said cuss in context. So I just kind of have some bullet points here that would be included in a good description. So I'm saying, from the probability distribution, we can see that the median is about 8. There are no unusual features. The graph is definitely left skewed with a single peak at 9. And as far as the spread, I'm saying that the Epgar scores vary from 0 to 10, but most of the scores are between 4 and 10. Part C says that doctors decided that Epgar scores of 7 or higher indicate a healthy newborn baby. What's the probability that a randomly selected baby is healthy? All right, so this is saying what's the probability that our random variable, capital X, is greater than or equal to 7. So what would this be equal to? Well, we can just sum these values. So it'd be good practice then, once you have your decimal, to give a sentence. So I'd say we have about a 91% chance of choosing a healthy baby. Next, we're supposed to find and interpret the expected value of x. So the expected value is equal to the mean of x, which is equal to each outcome times the chance of it occurring. And again, I'm not going to write this all out. And I can put this in my calculator. You can use your one variable stat feature. Have your data in list 1 and list 2. Or by hand. And I would say that this Epgar score is of many, many randomly chosen babies. Okay, and lastly, we're told to calculate and interpret the standard deviation of x. So I'm going to need my data here, so let me just shrink to give myself some space to write. Okay. Again, this formula is on your formula sheet. So sigma of x, and I usually again start with my variance, so that just means I'm going to drop my square root, is I take each random variable, or each outcome of each random variable, and I subtract my mean, the 8.128, I square it, and I multiply that times the probability. I'm doing the summation of this. So I take my next random outcome, 1 minus the mean, 8.128, I square it and multiply it by the probability of that happening. and I'm going to go all the way up to my last one where I would take 10 minus 8.128, square it, 0.00, or let me fix that, 0.053, right? So this would take a little bit of time to type in your calculator. I've done this. When I get this, my variance is 2.066. Now to get my standard deviation, I just square root that. And again, I'm rounding as little as possible, so 1.437. So let's interpret that standard deviation. So a randomly selected newborn's Epgar score will typically differ from the mean of 8.128 by about 1.4 units. Okay, I would encourage you to try to do this using your one variable stat in your calculator as well.